In this video, we're going to be talking about the rotational form of work. So as we know, this rotational form of work of the work energy theorem, which you're familiar with. So what is this variant? Well, this variant is just tau times delta theta, which is the change in angular displacement, and that's going to equal to 1/2 times the inertia times the angular acceleration minus 1/2 times the inertia times angular acceleration initial squared. And so where does this come from? What is the normal work energy theorem form that we know? So that's just F delta x, and then we know W is equal to, the work is going to be 1/2 mv squared minus 1/2 mv initial squared. And so what is something important that we had to know about this? Well, what we need to know is that you should not use, don't use work energy solving process for this, because this type of work is only causing rotational kinetic energy. And if you apply our standard work energy process, it'll give you the wrong answer. So what does this mean? So you can think of it like, if you have a graph like this, the area under, okay, so area is going to equal to rotational work, and this is going to be the graph of tau, okay, tau and against delta theta, because it's similar to the angular displacement curve, to angular displacement. And what are things that we should note about this is you don't use don't use this for, what you don't use this for is changes in gravitational potential energy or spring potential energy. And why is this? Well, that's because these forms of energy have no rotational work equivalent. So it just means that it's just purely translational. And if you try to apply it outside the proper context, it'll lead to the incorrect result, because the derivations and physical meanings differ. Another thing you should note is that if torque varies with angular displacement, you cannot simply multiply torque by angular displacement. Instead, what you do is calculate this is what you do here. You find the area under the torque versus angular displacement curve to find the actual work done. So in summary, when you use this formula, this formula is only used to Analyze torque changes with rotational kinetic energy of an object. What you do is you avoid mixing it with linear work methods involving potential energy. So this is how you keep things your problem solving correct in rotational dynamics. So let's look at a example of this. So let's say we have a problem like this. Say we have a wall and then we have a pulley system like this, and it's at a radius r, and we have a downward force that's pulling like this. So a string is wrapped around the pulley and it is pulled constantly downward. This F is going to be constant and it's going to be equal to 50 newtons. And the radius is just going to as r here, as we can see. And then we also know that we'll also define rotational inertia is going to equal to 0.10 for the pulley. And then let's say that the the radius r is rotational I. That's gonna the radius rotational I is gonna be 0.10 meters, and then the pulley's rotational I is gonna be 2.5 times 10 to the negative 3 meters squared. So, and let's assume that the string doesn't slip. So now what we want to find is what's the angular velocity of the pulley after 1.0 meters of string has unwound. And let's assume that pulley starts from, so how do we tackle this? Well, what you're gonna do is, so the work done by the string, it doesn't have a rotational form. Work done by string doesn't have a rotational form. So you need to use you can also use the linear form. And they'll kind of give you both of the same answers. So what we can do is we know that F delta X is equal to delta E. Even though we know that that'll always give you the change in energy. And even though the rope doesn't really have any mass, but the rope is massless. We have to remember that. So the system, we can just define the system is just equal to the pulley. So what we can do is just we have 50 times 1 meter of the pulley, because there's no work being done by the rope. So it's just going to be displacement. So we can say that this is also like delta X. So what kind of energy are we talking about? We're talking about kinetic energy. So it's going to be spinning energy. So what we can do is we can rewrite this. I'm just going to write this as delta E. So we can rewrite this as 1/2. We use the formula for the cylinder, which is just going to be 1/2 WF squared. And this is going to be the theorem we were talking about up here, the work energy theorem, which is we're using the we're gonna be using this form because this is what is it called? This is a rotational form of work, so we have to use the rotational from the work energy theorem. This is the example we're talking about. 1/2 1 W initial squared, and we know it starts from rest, so then we can cancel this out. So now we just solve for the angular velocity. So the easiest way to do this is we have WF is going to equal to 2 times 50 times 1, which is rotational inertia, is also 2.5 times 10 to the negative 3 that we had. And then we take the square root of that because we had to rearrange that just for WF. So then if we calculate this using our calculator, we're going to have, one second, we're going to have 200 radians per second right there. Now, the second way we can do this is with the other formula. Tau delta theta is equal to 1/2 IWF squared minus 1/2 angular acceleration squared, and you know that this is going to be 0. So now if you draw the r vector, well, the torque is going to be the force times r times theta, so F times r times delta theta. Well, we know that, and we also know we're traveling over here, so we know that, again, the radius is going to be the same in both directions. This is still going to be r, and then we know the distance is just going to be, equal to the distance traveled. So d is going to equal to r delta theta. So down here, we can continue by saying that, well, we know that angular displacement is going to, we know that angular displacement is going to be equal to d over r. And that's also going to be equal to 1 times 0, which is just 1 times 0 minus 1. So that's just going to be 10. So now we can rewrite this down here, plugging that all in. We're going to have 50 times 0.1 times 10. It's going to equal to 1/2 I times WF squared. This is going to equal to 50. That's going to equal to 1/2 WF squared. And yeah, that's going to give you the same answer if you just rewrite that.